Now we'll talk about specifying parameters. For Phase 2, our goal is to massively simplify our parameter and test descriptions. We've made it extremely easy to define JSON parameters and test scenarios in the test harness. Since the challenge problems in Phase 2 have many more parameters to define, we want to ensure that closing the loop with each performer team is effortless for everyone, for instance by sharing and collaborating via code on GitHub. We hope that we can quickly integrate our new parameter definition approach with your teams over the next couple of months. Then, we can work in concert with your teams to explore a wider class of interesting test inputs, not limited to JSON. This might include anything from generating code to simulating RF waveforms. Also, the automaton model used in Phase 1 is gone in Phase 2. So let's take a look at how we're proposing to design tests in Phase 2. First, we'll demo our new lightweight parameter representation, and then we'll walk through a simple DSL that we've created for test specification. We're releasing a first draft of both of these now, and through regular updates we hope to provide useful tools for your research in Phase 2. Let's start with parameters. We've switched to representing everything as a random variable. We're sampling JSON directly from these random variables. We support rich statistical models, and our new representation is simple to understand and share with teams. We hope that this will make your integration with the test harness a cinch, and our parameter representation also supports real-time dashboards during test execution, which is detailed in another video. Let's look at a quick example. We have a full video that covers our example mock app, but we'll just focus on the parameter specification in this video. The mock app simulates a robot driving around. Let's look at a couple of the parameters. Here's a tiny JSON schema for 3 parameters, a drop in the current battery charge, a change in terrain, and an increase in temperature. We represent these 3 parameters using 3 distributions, a uniform distribution with left and right boundaries, an enum representing possible states, and a normal distribution with mean and standard deviations. Then, we wrap up these 3 parameters into a single random variable that produces JSON. In our command line interpreter, we draw 2 samples from this random variable and print the JSON out. We can see that the value for each parameter has been drawn from their own distributions. Now, let's look at how the mock application uses these parameters. After the test harness draws the JSON message from the parameter's random variable, the test harness posts it to the perturb endpoint of the mock application. The mock application decodes the JSON body of the message into a hash map and proceeds to perturb the internal state of the system using the values for each parameter. Our test harness also reads parameters directly from YAML files, and it auto-generates plots of the parameter distributions inside our Phase 2 dashboard. Here we specified battery temperature and wind speed distributions as YAML. In order to explore different regions of the state space, you can just edit the YAML file and rerun a queue of tests. Editing the YAML file will also regenerate the plots, allowing for quick visual inspection before test execution. We also support dependencies among parameters. This example shows nested dependencies for one field of a JSON message, and we can also represent dependencies across JSON fields or even across multiple tests. In this way, we can support arbitrarily complex distributions of JSON, which remain easy to reason about and use. All of this allows for easy incorporation of statistical models as a part of the test. We support any type of distribution, and when sampling, we can incorporate statistical methods. For instance, we can hold one variable fixed while varying others, or we can use Monte Carlo methods, for instance, if you wanted to uniformly sample the state space, but vary the density between points. We hope to iterate closely with your teams on parameter modeling. Now, let's switch to authoring tests. We've prototyped a new, simple DSL for defining the perturbations that constitute a test. Let's see an example. Here's a short script for a test written in our DSL. The first instruction blocks until the system under test posts to the test harness's ready handler. This indicates to the test harness that the SUT has received the initial parameters for the current test. We then allow the system to run for 5 minutes with these parameters. Next, we log a message to the dashboard and schedule 10 perturbations. Inside of the loop, we choose a random variable to use for the perturbation. We sample JSON from this random variable, and we log the choice in our dashboard and send the JSON message to the perturb handler of the system under test. Finally, we sleep for 5 minutes and then loop back. Once the 10 perturbations are complete, we wait for the system under test to post a verdict to the test harness. These tests are easy to modify. For instance, if we wanted to instead change the test to only perturb the battery level, it's a one-line change. Let's also change the test to draw the number of perturbations from another distribution. Here, numpy is another choice from a random variable, which is part of the initial parameters sent to the SUT. If the SUT requires a variable amount of time to configure, we can instead pause until the SUT tells the test harness that it's configured, as shown here. We can also represent an infinite stream of perturbations, shown here using the terrain random variable. We're eager to hear your ideas on what to add next. For instance, we spiked out an interactive user interface for the test harness, allowing us to dynamically change parameter values right from the dashboard. In Phase 2, our goal is to work in concert with each performer team to design a suite of powerful tools for research on adaptive systems. We want to minimize or eliminate the time spent doing rote software engineering and integration so that we can focus on driving the research forward. What we've shown in this video is 1 month of our internal prototyping. In Phase 2, we want to pick up the pace and continuously deliver new features.